Hi everybody, this video has sound. Hopefully everybody can hear it. And those people that can't hear sound, hopefully they're making sure that they set everything up so that they can hear the sound. This is Chapter 3, Section 3, otherwise known as 3.3, in the Chapter 3 Study Guide for Geometry. We're going to start with some definitions. A paragraph proof is a little different than a two-column proof. The proofs that we usually do in this class in geometry are called the two-column proofs, where we have a statement on the left-hand column and we state the reasons for the corresponding statements in the right-hand column. So we kind of get this two-column effect, and it looks like this. Here's an example from section 3.2. Now, a paragraph proof is still a logical sequence of statements that is demonstrating something to be true based on some given information. However, the paragraph proof is a proof that looks like a paragraph. So basically, your reasons and your statements and your reasons are just kind of written all together as if they were a statement. Like you would say, oh, angles 1 and 2 add up to 180 degrees, and the reason would be they are supplementary. Something like that. But you would just state that all as one large sentence, and then you move on to the next sentence. If-then form, it's how our logical statements are made. We talked about them, I think, in the previous chapter. It might be chapter 2, yeah. But basically, if-then form is oftentimes how we can state theorems and postulates. You know, if two angles add up to 90 degrees, then they are complementary, things like that. So you're going to see a lot of our postulates and theorems in this book are stated in that way. Now, the converse is when you change around the original. So if the original if-then form says, let's see, if an angle is 90 degrees, then it is a right angle. The converse of that would be if an angle is a right angle, then it measures, or it is, 90 degrees. So the converse, you know, when we're stating things that are always true together, the original if-then form is just as good as the converse. Now remember, when we're making proofs, there's step 1, step 2, step 3, step 4. So sometimes we'll be given, you know, a 90-degree angle, and it will be helpful for us to then conclude that it's right angle, or vice versa. Many times it would be this. If it's given to us that something's a right angle and we need to state it specifically as 90 degrees, it would be better to state the converse on our reason side of our proof. So here's an example of a converse. Before, we learned something that said that if lines are parallel, that if you have a set of parallel lines, that would be this one and this one. It's stated here as J and K being parallel. Then the corresponding angles, here would be one example of a corresponding pair, are congruent. But you can see this states it exactly the other way around. This is the converse of the corresponding angles postulate. The converse just states it in the opposite order. The converse says if two lines are cut by a transversal so that the corresponding angles are congruent, comma, then the lines are parallel. So it's stating a truth. These two things have to be true together, but it's just stating it in the other order of the original if-then format. Okay? So let me see if I can find the corresponding angles postulate. There it is. Back here on this page, this one says if two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent. Whereas postulate 16 says, if two lines are cut by transversals so the corresponding angles are congruent, then the lines are parallel. It's just stating the corresponding angle congruence and the parallel lines in the opposite order in the if-then statement. Okay, so I would be willing to guess that the first proof has something to do with congruent angles and perhaps even corresponding angles. Well, let's see what we have to do here. Given that the measure of angle 1 and the measure of angle 7 are equal, I'm going to state that on my first line. We almost always start with just what they've given us. Sometimes they give us more than one thing, and some people like to break up the amount of given information and state them part of it up here and then part of it elsewhere in the proof because it logically makes more sense. But for the most part, we're just going to be stating on the first line whatever the given information is. Okay, well, what do they want us to do? They want us to prove that line A and line B are parallel. This is the symbol for parallel. Well, if I could prove that these two angles here are congruent, I just mark them congruent. If I could prove that to be true, then by the corresponding angles converse, then I could show the lines are parallel, because that's what the converse says. When you show that corresponding angles are congruent, then those lines are parallel. Okay, well, having the same measure is almost exactly the same as congruence. We just have to write it in the new way. We just have to say that angle 1 is congruent to angle 7, and we know that because their measures are the same. That's what congruent angles are. That's the definition of congruent angles. When two angles have the same measure, then they're congruent. This is one of those reasons that it kind of automatically flows from this statement. Congruent angles have the same measure, and angles that have the same measure are congruent. And whenever you want to change the format from equality of measurement to congruency or back again, you can always state the basic definition that holds these two statements together always. Well, really, that was the only connecting concept that I needed. I just simply needed to prove, if I wanted to use postulate 16, that angle 1 and angle 7 are congruent, and I have. So now I can go ahead and say the statement that they asked me to prove. Line A is indeed parallel to line B, reason being postulate 16. Now I'm going to list it, I'm going to write it as the full formal name, the corresponding angles converse. The reason why I'm writing it like this is that our textbook happens to call it postulate 16 in chapter 3, but if you're somewhere else and you call it postulate 16, not a whole lot of people are going to know what you're talking about. However, if you call it the corresponding angles converse, that'll be a lot more familiar and more universally understood. Okay, next page. Starts off with a question. How do we make sure that a line is parallel? Well, make corresponding angles congruent. Well, I think they wanted to ask, how do you make sure lines are parallel, not make sure a line is parallel? So let's see. Congruent is the same concept as equal in measure. So let's see. Find the value of x that makes line M parallel to line N. Well, we have a pair of corresponding angles. We've got one here and one here, right? They're in the upper right-hand corner of the intersection of each position here. So if I wanted to show that these two lines are parallel, then I would have to demonstrate that those two corresponding angles are equal in measure. So the value of x that would get you there would be the value of x that shows that 2x plus 3 is equal to 71. So I will go ahead and solve this. I'm going to subtract 3 on both sides. then divide both sides by 2. So x equals 34. Now, when you take your quiz, the C-level questions are going to look very, 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 very much like this. Now, sometimes you're going to have to think about corresponding angles. Sometimes there'll be alternate interior angles, which have also a congruence relationship. Sometimes there'll be, alternate exterior angles, which are congruent. And sometimes they're going to be consecutive interior angles. Now, consecutive interior angles do not have the same measure. That would be, for example, if I cover this example up, right here and right here. So this corner and this corner. Those two do not equal each other, but they are supplementary. They add up to 180. So we wouldn't say that they're equal. If we wanted to solve for x, we would do something different. We would say whatever this angle is labeled plus whatever that angle is labeled equals 180, and then we would solve that. It'd have more elements in that equation, but you could still set it up correctly and solve it. Now, the second example is still having to do with corresponding angles. In this intersection, we've got an angle labeled in the upper left-hand corner, and same thing here, this one's in the upper left-hand corner. And in order to make A and B lines parallel, those two corresponding angles would have to be equal in measure. So that's how I would solve this. I would set up that equivalence relationship, and I'd figure out what that x value would have to be in order for that to be true by solving the equation. In this case, x equals 21. Okay. Just a review of some other theorems and postulates having to do with parallel lines and a transversal line cutting through. Theorem 3.4 says that if two lines are cut by a transversal line, that's this line cutting through, so that the alternate interior angles, here's one pair of alternate interior, here would be a second pair of this one and that one. If the alternate interior angles are congruent, then the lines are parallel. Now, I'm sure there was an alternate interior angles original postulate or theorem back here on this page. It says that if two angles lie between two lines on the opposite sides of a transversal, then they are called alternate interior angles. Now, that one doesn't talk about their parallel nature, does it, of those two lines? So I'm just trying to find if we stated the theorem in the original way. Yes, alternate interior angles theorem. There we go. So this one says if two lines are parallel, two parallel lines are cut by a transversal, then the pairs of alternate interior angles are congruent. Now you can see that the converse just simply states it the other way around. If two lines cut by a transversal so that the alternate interior angles are congruent, then the lines are parallel. So it changes the if part and the then part backwards. That's a converse. That's what it does. It's an if-then statement stated the other way around. The alternate exterior angles converse takes this one, the alternate exterior angles theorem. If two lines, parallel lines exist, then and a line of transversal exists, then the pairs of alternate exterior angles are congruent. And this one says if the alternate exterior angles are congruent, then the lines are parallel. So it's just making the same statement the other way around. Now, alternate exterior angles. Exterior means the outside, and I always think of the two parallel lines being a road. And if you're on the inside of the road, you're traveling somewhere in this space here. And if you're on the exterior of the road, that means you drove off the road. The exterior would be up here or down here, right? So alternate means on opposite sides of the transversal. So angles 1 and 8 would be exterior of the roadway, but they'd be on the alternate sides of the transversal line. So alternate exterior angles would be this. There'd be another pair here and here. Whereas alternate interior angles, again, if this is my roadway space, on the inside of the road would be in here somewhere, and the alternate positions would be one on one side of the transversal and one on the other. There's another alternate interior pair right here. So let's see if we can apply these. Oh, got one more converse to talk about. This is the one that I think a lot of students forget about. They're so used to saying that the angles are equal, 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 equal. All of a sudden this one crops up and they state that they're equal, but they're not equal. This kind of relationship here between this angle and this angle is not a congruence relationship, it's a supplementary relationship. Remember, that means that they add up to 180 degrees. Okay? So consecutive interior angles, remember this is my roadway, then this would be inside the road here between the lines. Consecutive means the same side of your transversal line. So angles 3 and 5 are definitely consecutive interior angles, or this one and this one would be another pair of consecutive interior angles because they'd be on the same side of the transversal but inside the road, interior. So this converse says that if you have consecutive interior angles that are supplementary, then the lines are parallel. Okay, so the converses of these special types of angle theorems help us prove things are parallel. You can see the then part on all of these, then you've got things that are parallel. Then lines are parallel, then lines are parallel. So if we're trying in a proof to demonstrate lines that are parallel, we would be looking for some sort of converse of either corresponding angles, alternate interior angles, alternate exterior angles, or consecutive interior angles, because the converses of these four demonstrate parallel lines exist. So here's a proof that shows that. We've got lines A and B that look like they could be parallel, but we have to prove that, right? That's what we want to logically conclude. And they want to first state that angle 1 and angle 4 are supplementary. So I'm just going to go ahead and write that in my given line. Angle 1 and angle 4 are supplementary. Okay. Well, the reason being, it was given to me. I can assume that to be true. Now, if angles 1 and 4 are supplementary, well, I don't know. Let's look at the diagram and state things that we know for sure are true. Well, I would say that angles 1 and 2 are supplementary. Do you see that? Because they form a straight angle pair from here to here. I would say that angles 2 and 3 are supplementary because they form a straight angle pair. They're called a linear pair. They go from one side of a straight line over the other when you combine them together. And the only other thing I can think of is that angles 1 and 3 are equal to one another because they form a vertical pair. Two angles that are on opposite corners of an intersection are going to be congruent, called a vertical pair. Okay. Can I use any of that information to somehow prove that A and B are parallel? Well, not really sure. If I have, for example, if I can prove that 2 and 4 are congruent, then I could use the corresponding angles theorem to go through and say, hey, yeah, 2 and 4 are congruent, therefore line A must be parallel to line B. Or if I could prove 3 and 4 are supplementary, then I could prove line A and B are parallel because of the consecutive interior angles theorem. So what could I do? Well, there's a couple different ways that you could think about this. I've stated a lot of things that I know that are true about the diagram. I think what I'm going to do is I'm going to create a link of congruence between angles 1 and 3 with the vertical angle theorem. And then, since angle 1 and angle 3 are congruent, then I can restate this statement saying that I'm going to substitute angle 4 or angle 1 out and put in angle 3 because of substitution. Any two things that are congruent, one can be replaced with the other in any statement. And then once I have angle 3 replaced here instead of angle 1, I'll have the statement that angles 3 and angle 4 are supplementary, and then I can use theorem 3.6 to say, hey, I have two consecutive interior angles that are supplementary. Therefore, my final conclusion is that the lines are parallel. So, 2 is that angle 1 is congruent to angle 3 by the vertical angles congruence theorem. Oops. Okay. And then here I'm going to use some substitution. I'm going to take my original statement, I'm going to take out angle 1. In its place, I'm going to put in angle 3. I'm just rewriting the original statement with a substitution. And then finally, because angles 3 and 4 are congruent, and I know that they are a consecutive interior pair, that line A must be parallel to line B because of this theorem up here. It's called the consecutive interior angle converse. Page 11 says, solve a real-world problem. How can you tell the sides of the flag are parallel? So basically they're saying, how do you know this line and this line are parallel lines? Well, you can see that this angle right here is marked congruent with this angle right there. Here's your transversal line, and those two angles are on the opposite side. So those are called alternate positions. And they are on the inside. If these two lines form the boundaries of the road, that would be on the inside of the road. So that would be an interior pair. Now, if we knew they were parallel and we were proving these congruent, we could use the alternate interior angles theorem. However, here we know they're congruent and we want to prove the lines are parallel, so that would be using the converse. Now we have a whole lot of examples here on this page of and the next. This is kind of a long section. I'm not going to do everything, but I'm just going to hit one so that we can apply each theorem at least once. So here we go. Is it possible to prove the lines parallel? Well, this angle right here is 58. This angle is 122. And they are in positions here and here. Now, these two are called consecutive interior angles. And if these two lines are parallel, then those should be add up to 180 degrees. So if I add up 58 and 122, do I get 180? Absolutely. So according to the consecutive interior angles converse, I can show those lines are parallel. This one, these two together, 60 and 25, for that amount, gives you 85 degrees. And then over here we can see this part is also 85 degrees. So if this angle and this angle are congruent because they both measure 85 degrees, are those two lines parallel? Yes, we can demonstrate that because these are in alternate interior positions. So by the alternate on opposite sides of the transversal, interior on the inside of my roadway, angles converse, then I can show that lines P and Q are parallel. This is 120 degrees. This would be, if I added up 82 and 40, you'd get 122 degrees. Those two are not congruent, so those two lines would not be parallel. These angles are called a corresponding pair, so if they were congruent in these two positions, then the lines would be parallel. But since they're not, we can definitively say that those lines could not be parallel. Okay. So, let's do a few of these. If I have an angle here is 100 degrees, and an angle here that's 2x, well, that is not really a pair of anything. They're not corresponding, they're not alternate interior, they're not alternate exterior, they're not consecutive interior. Those two are nothing. So, here's what I would do. I would say, well, is there any pair that I could make? I know that this corner and this corner are congruent, for example, because they're vertical pair, right? Angles that are across from one another in an intersection must be congruent. So if this is 100 degrees, then this right here would also be 100 degrees, right? Now, if I look at this pair, is this anything? Well, yes. These two angles are on the interior side of the roadway, and they are on the same side of the transversal. That's called a consecutive interior pair. Now, that's what these are. And what is the relationship between these two angles? Well, they are not congruent, they're not equal, but they are supplementary. They add up to be 180 degrees. So, I'm just going to focus on these two as a supplementary pair, and I'll say if I add 2x plus 100, then I will get 180 degrees. So to find the value of x, now that I have the relationship established in equation format, I just do what I normally do to solve an equation. And x equals 90. Why do I have... Oh, I see. I wrote an extra 1 right here. I'm confusing myself. There we go. This is 80 degrees, not 180. And that would be 40. Okay. Okay. The next two angles are here and here. That would be a corresponding pair. They're in exactly the same position. This is in the upper right-hand corner of the intersection. This is also in the upper right-hand corner of the intersection. So those are corresponding, and therefore they would be equal in measure. So I could say that x plus 1 would be equal to 110 degrees. So simply solving by subtracting 1 gives us an x value of 109 degrees, or 109. Okay, how about these two? This one's 80 degrees and this one's labeled as x minus 15. Are they congruent? No. This is the one category that is not a congruence relationship of the 5 different types of pairs of angles that we can name. This is a consecutive interior pair. These two angles have a relationship. It is a supplementary relationship, not a congruence relationship. So I can say that the bottom angle, x minus 15, if I add that to the higher angle, 80, then I know that they're going to add up to 180. So if I add these two together, I get 65. And then if I subtract 65 on both sides, I'll get x equals 115. Okay, well here I have an angle here and an angle here. Those two are on alternate sides of the transversal, but they're on the interior part of the roadway, so these would be called an alternate interior pair. That relationship is congruence. So 6x minus 44 would be equal to 4x. So I would solve this by subtracting 4x on both sides and then adding 44 on both sides and then dividing both sides by 2. Now I know I started off by saying I wasn't going to do all of them, but I think I will. I'll do the last two. Okay, we have a position here and here. Each of these angles is in the upper left-hand corner of the intersection that it's connected to. So that is a congruence relationship. So I can say that this angle down here, 7x plus 13, would be equal to this angle up here, 5x plus 23. So I'm going to subtract 5x on both sides, which gives me 2x plus 13 equals 23. Then I'm going to subtract 13 on both sides, which gives me 2x equals 10. And then if I divide both sides by 2, x equals 5. Okay, and then the last example is this angle right here and that angle right there. Those two angles are next to each other on the inside of the road, and they do not have a congruence relationship. Hopefully by now you could tell me that they have a supplementary relationship, meaning that when you add the two angles together, this angle x plus the angle up there, which is x plus 20, that they're going to add up to 180 degrees. Now the way we solve this when we have variables on the same side is we simply combine like terms, so we get 2x because this is 1x and 1x. And I would then subtract 20 on both sides, so I'd get 2x equals 160. And then dividing both sides by 2 gives me 80 for my x value. Okay, let's see what we've got on the next page. These are talking about a lot about the transitive property here. Let's do okay. Example 4 is talking about telephone poles, and number 4 is talking about slats on blinds. Well, I think what we can do is just talk a little bit about the transitive property. Okay. I think this is a better example over here, number 13. Number 13 illustrates the same concept as these two, so I think I'm going to skip this and just talk about the transitive property theorem down here, and then use the gardens example, number 13, over here. So I don't think I need to state it more than one time. Okay. So if two lines are parallel to the same line, then they are parallel to each other. It's basically the transitive property of parallel lines. So that means if P is parallel to Q and Q is parallel to R, then P would be parallel to R. So Number 13 illustrates this idea where you have 5 rows of vegetables, row 1, row 2, row 3, row 4, and row 5. And each row is parallel to the row next to it. So explain why the first row is parallel to the last row. Well, I could say that row 1 is parallel to row 2 because they're next to each other. And row 2 is parallel to row 3 because those two are next to each other. So, according to this property here, any two lines that are parallel to the same line would have to be parallel to each other. Row 1 would have to be parallel to row 3, right? Okay. Row 3 is parallel to row 4 because they're next to each other. And row 4 is parallel to row 5 because they're next to each other. So, according to the transitive property of parallel lines, row 3 would have to be parallel to row 5. Now, if we take these last two statements together as something that's true, if I know that row 1 is parallel to row 3, and row 3 is parallel to row 5, so since row 1 is parallel to row 3, and row 3 is parallel to row 5, then I can say that row 1 must be parallel to row 5. So let's figure this out. If two lines are cut by a transversal so that the alternate interior angles are blank, then the lines are parallel. So if you have two lines that you want to prove parallel, you've got a transversal, and the alternate interior angles are what? Well, these would have to be congruent in order for those lines to be proven parallel. Alternate interior angles. This will be another pair of alternate interior angles. This one right here, paired with this one right here. If two lines are cut by a transversal such that the consecutive interior angles are, consecutive interior angles will be the ones on the inside, but they're next to each other, they're not opposite. So this right here would be a consecutive interior pair, or the ones on the other side, these two would be a consecutive interior pair. Now this type of pair, you'd have to not prove them congruent. No, these two would be supplementary because they add up to 180 degrees. This is the one that people often forget because they're so used to stating everything as congruent. So be careful with that one. Number 12. Number 12 says if you have two lines cut by a transversal line, the corresponding angles are what? Well, you have four pairs of corresponding angles. You've got angle 1 and angle 5 are corresponding. You've got angle 2 and angle 6 are corresponding. You've got angles 3 and 7 that are corresponding, and you've got angles 4 and 8 that are corresponding. So any pair of these that we can prove are congruent would demonstrate these two lines are parallel. Oh my goodness, the final example of section 3.3. Here we go. We want to create a two-column proof. So we're going to have statements of on the left side and reasons on the right side. That help us logically eventually get to proving that lines P and R are parallel. I'm going to start with the given information. I'm just going to write this one though. I'm just going to use one of my givens, that lines G and H are parallel. Now, if G and H are parallel, what do we know? Well, I know that angle 1 and angle 3 would have to be congruent because they're corresponding angles alongside these two parallel lines, G and H. I might be able to prove some vertical angles. I don't know if that would help me, this one and this one and this one and that one, but since these aren't really labeled, I'm assuming that I'm not going to use a vertical angle theorem here. So how do I demonstrate P and R are parallel? Well, the only two angles that I can think of that might work is 3 and 2. 3 and 2 are both on the same transversal and sitting on those two parallel lines that we want to prove that are parallel. And they are on alternate exterior positions. So if I can prove that angles 3 and angle 2 are congruent, then by the alternate exterior angles converse, I would be able to say that lines P and R are parallel. Okay, so how do I get there? Well, I think first I'll prove that 1 and 3 must be congruent by the corresponding angles congruence theorem. Then I could probably say that I can use this given information here, that angles 1 and 2 are congruent. And then if I know 1 is congruent to 3 and 1 is also congruent to 2, that by the transitive property 3 must be congruent to 2. So let's go ahead and start writing this down. Because G and H are parallel, angles 1 and 3 are congruent. The corresponding angles congruence theorem. And then what did I say? Well, then I was going to grab the other given piece of information. Now you could actually state this up here in the given as well, but some people list, you know, parts of the given on different lines. And then I talked about the transitive property. I want to somehow link angles 3 and 2 as being congruent because they're alternate exterior angles. And then I'd be able to jump ahead and say, hey, P and R are parallel lines. So if angle 3 is congruent to angle 1, and angle 1 is congruent to angle 2, then by the transitive property of angles, angle 3 would have to be congruent to angle 2, wouldn't it? So the transitive property. And so finally we could say that we have a alternate exterior angle pair. We know that they're congruent. So I'm going to go ahead and say that line P and line R are parallel because of the alternate exterior angles converse. Remember, the converse postulates and theorems are the things that help us state things are two lines are parallel.